Hi everyone, my name is Nilesh. I'm a master's student from the EC department, and my topic for the presentation is end-to-end lane detection, multi-lane detection. So, camera-based lane detection is an important step towards environmental perception as it allows the car to properly position itself within the road lane lines. So, accurate localization of the vehicle within the road lane lines is extremely important to fully realize fully autonomous vehicles, and is also important for a variety of other applications like uh, lane departure or motion planning, etc. So one of the most famous lane detection algorithms out there is the lane net. So this is the lane net architecture. It consists of two branches, the segmentation branch and the pixel embedding branch. Both these branches, they have the same encoder. They are different decoders. It is based on the ENet architecture. In the ENet architecture, the number of parameters in the encoder is much higher than that of the decoder. So sharing the encoder between both the branches can lead to unsatisfactory results. So only the first two stages of the encoder is shared, and the third stage of the encoder and the decoder is different for both the branches. So a segmentation branch, it generates a one-dimensional binary lane mask output, which consists of two classes, and these classes denote whether a lane line exists or it doesn't exist. And the pixel embedding branch, it generates an n-dimensional output image where each and every lane instance is represented by a particular pixel value. So since there are four different lane instances over here, it's represented by four different pixel values. Both of these are passed to a clustering algorithm called dbscan, which clusters all the lane coordinates belonging to the same pixel together. Thus, there are four different clusters, each representing one lane instance. The backbone network is BizNet version 2, and the loss functions for the segmentation branch is binary cross entropy. For the pixel embedding branch is discriminative loss function, which is a clustering loss function. By using this loss function, the instance embedding branch is trained to output an embedding for each lane pixel so that the distance between pixel embeddings belonging to the same lane is small, whereas the distance between lane embeddings belonging to a different pixel is large. This ensures pixel embeddings of the same lane will cluster together, forming unique clusters per lane. The dataset used is a TU-simple dataset which consists of 6,000 road images of US highways. So this is the overall architecture of the implementation, and this is the lane net architecture. The next stage is to convert this image into its bird's eye view or perspective transform in order to fit the lane lines, in order to account for lane curvature. So in the paper, they use another neural network called HNet, which basically predicts a homography matrix to transform the original image into its perspective transform, and this is better than a fixed perspective transform or bird's eye view conversion, because it accounts for the changes in the plane of the road. So the first step of implementation is to use the pre-trained model on the TU-simple dataset and visualize the output. So we can see this is the binary lane segmentation output, this is the pixel embedding output, and this is the post-processed image. So the next stage was to create my own dataset. So I created an annotation tool that helped me automate the process of annotation and also generate labels that were the exact same as that of the TU-simple dataset. So since the amount of data that I generated was very less, I loaded the weights of the pre-trained model and trained on top of that. So these are the outputs. This is the binary lane segmentation output, pixel embedding output, and the post-process image. And also I modified the post-processing code a little bit so that the lane in which the vehicle is traveling is highlighted. So the next stage of implementation was not only to predict whether a lane line exists or doesn't exist, but also to predict, to differentiate or to classify the different lane lines into white lane lines, yellow lane lines, or road edges. So again, I created my own custom dataset for that, and this is how the labels work for the segmentation branch. As you can see, so the white lane lines and the yellow lane lines and the road edges are denoted by different pixel values from 0 to 255. So the goal was to load the weights of the train model except up until the last layer for the segmentation branch, and freeze those weights and train the last layer of the segmentation branch, which basically consists of 4 classes instead of 2 classes. Each of these these classes represent white lane lines, yellow lane lines, road edges, and no lane lines. Unfortunately, when I tried to train only the last layer of the segmentation branch, the training loss did not converge. So I loaded the weights of the pre-trained model, and I trained all the parameters. But this was the output I got, and I think this can be attributed to the large number of parameters that were supposed to be trained, and the deficit of images in the dataset. This is my project. Thank you for listening.